looking at this next example, we've got a cube root and the fourth root of complex numbers. So we'll start with A. Find cube root of 8i. So another way of writing that is z cubed equals to 8i. Next step, let z equal to r cis theta. In this case, we're writing r is because we've got an 8 in front of the I. So we write that as r cubed, de Morph's theorem, brackets cis 3 theta equals to 8 brackets I. If we write it in monarch form, we get cos 90 is 0, sin 90 is 1. So we can go cis pi upon 2, we'll just write the 2k pi over here. Make it a little bit easier. Now we can equate the separate terms. We've got r cubed is 8, so r then equals to cube root of 8 is just 2, and we can equate these separately. Cis cancels out, we get 3 theta equals to pi upon 2 plus 2k pi. Divide both sides by 3. We get theta is then pi upon 6 plus 2k pi all upon 3 multiplied by that by 2. We get pi plus 4k pi upon 6, so we get pi plus 4k pi all upon 6. We can factor out the pi. Theta is just 4k plus 1 pi upon 6. So that's what theta equals to. Principal argument, coming back to that, negative pi, so we write that down over here. So we have negative pi less than this value over here. So this is basically argument, so we've got 4k plus 1 pi upon 6 is less than or equal to, don't forget that, pi. That equals to that. Next step, multiply both sides by 6 and divide both sides by pi. The pi and pi cancel out. So we get negative 6 is less than 4k plus 1, which is less than or equal to 6. We've got to be careful here. We need to know for what values of k do we get for the argument that stays within negative 6 and 6. If we sub in k equals to 0, is that between negative 6 and 6? Yeah, we get 1. If we sub in k equals to negative 1, negative 4 plus 1 is negative 3, which is between negative 6 and 6. If we sub in negative 2 is minus, 4 multiplied negative to negative 8 plus 1 negative 7. That is out of the principal argument. So, negative 2 is not a case for k. Same thing, go back to 1. Let k equal to 1. 4 times 1 is 4 plus 1 is 5. That's between negative 6 and 6. Yes, it is. K equals to 2. 4 times 2 is 8 plus 1, 9 out of the principal argument. Therefore, the values of k then, so the distinct solutions for this complex number lies when k equals to negative 1, 0 and 1. Now we can sub that into here, which then gives me z of 1 equals to 4 times negative 1 is negative 4 plus 1, negative 3 upon 6, which is negative 1 upon 2. So this then gives me 2 cis negative pi upon 2. First solution. We'll just leave it in monarch form for now. Z2. Same thing. 2 comes in front. Cis k equals to 0. Pi upon 6. And then Z3 equals to 2 cis 4 times 1 is 4 plus 1 is 5. 5 pi upon 6. So these are your three solutions in mod arc form, mind you, in mod arc form for this complex number here. Sorry, the square root of this complex number here, the three solutions. If you want to further go into writing this in Cartesian form, you can, but we'll just leave it at that for now. We'll go on to B, which is very similar, but a little bit different. So we've got z to the power of 4 equals to 1 plus root 3 I. So let's start. Similar approach. We'll take a similar approach. Z to the power of 4. Z to the power of 4. Same thing. Let z equal to r cis theta. We have r to the power of 4 cis 4 theta equals to, change this in mod arc form. 1 plus root 3. Modulus of that straight away is 2. We know that because if we go square root of 1 squared plus root 3 all squared is just root 3 and square cancel out. 1 plus 3, 4. Square root of that is 2. But in this case, for modulus, we always take the positive case, which is 2. Argument. Argument diagram. We've got root 3 around here, 1's around there. Something like that. Sorry, my bad. 1 would be here, root 3 would be here. Inverse tan of root 3 gives me, I believe it's 60 degrees. Root 3 is correct, 60 degrees. So I put that in, so this then gives me 2 brackets cis. We go pi on 3 bracket cis pi on 3 and then again plus 2k pi. Same thing, r to the power of 4 equals to 2 and then 4 theta equals to pi on 3 plus 2k pi. Correct? R to the power of 4, take the 4th root of 2, which is just 4th root of 2 equals to r. Sorry, I'll drop this Haken diagram out so you don't get confused. That's what r equals to. Now we go for theta. Theta then equals to pi, the bottom becomes 12, 1 upon 2 pi plus k pi upon 2, correct? 6 times 2 is 12 plus 6k pi all upon 12. That's right. Theta then equals to, we can take out 6k plus 1 pi all upon 12. Same thing. Come back into principal argument. Negative pi is less than 6k plus 1 pi upon 12 less than or equal to pi. Same thing, multiply both sides by 12, divide by pi. Negative 12 is less than 6k plus 1, which is less than or equal to 12. Same thing. For what values of k do we get? The argument is between negative 12 and 12. K equals to 0. 600? Yep. So tick when k equals to 0. K equals to 1. Yep. There's a solution there. 6 times 1 is 6 plus 1 is 7. K equals to negative 1. Negative 6 plus 1 is negative 5, correct? Negative 1. And k equals to 2. 6 times 2 is 12, plus 1, 13. Nope, not a solution. So k equals to negative 2. Mind you, negative 2 times 6 is negative 12, plus 1 is negative 11, which is a solution. Therefore, k then equals to negative 2 is a solution. Now what we do, same thing for the four roots, we go z. 1 equals to 4th root of 2, we have cis. Let k go to 0, we go pi on 12. Because 0, 0, 1 upon 12. Z2 we have fourth root of 2 cis 1 7 pound 12 Z to the power of, sorry, not to the power of, Z3. So I've got a habit of saying to the power all the time. I'm going to stop saying that. Negative 1, negative 5 on 12, so 4 root 2 cis negative 5 pi on 12, and then the last one, negative 11 pi on 12. So Z 4 root 2, fourth root of 2, we have cis negative 11 pi on 12. Again, these values will give us an ugly number if we change them into Cartesian form, so we'll just leave them in mod arc form. So these are the 4 solutions to this question here.